Assalamu alaikum everyone. So let us start. So we were talking about swing equation in the last class. We went through some of the assumptions and we saw that most of these assumptions are related to the disadvantages that we have while developing the classical model. Then we saw what is a typical example of SMIB. We saw the circuit diagram, and then we went to derive the swing equation. We saw what this signify. What is theta m, what is delta m? These things should be pretty clear by now. Yeah. Then we saw few easy equations, and then finally, this is where we stopped. So what was our last discussing point? We discussed that this quantity over here, this quantity over here, yeah, pretty much these two. Yeah. So these are mechanical quantities. So we are interested to convert those into our equivalent electrical quantities. Okay. So let's see how we can do that. So from there, after we have converted, again, we'll start with this equation that we have over here, and we will find the corresponding equivalent electrical model for the swing equation. So moving on, so let's take this example. Okay. So first of all, we have to know how mechanical angle and electrical angle behaves. Yeah. So what we have a two-pole system. As we can see, that we have a north pole, we have a south pole. So whatever is designated as N and S, can someone tell me that whether that is part of your rotor or part of your stator? N and S. So these are part of your rotor or stator?
Status.
Stator, sir.
Very good. So these are part of my stator. So which one is my rotor over here? Definitely this one. This is my rotor. So this one will rotate. But the north-south, the stator part will always remain constant. Okay. So if you just take the rotor out of this configuration on the right hand side, as you can see, that assume this is your rotor. You have just taken it out of the machine, out of your generator or synchronous generator that you have. Yeah. So very obvious, if this red color is your starting point, and if you rotate once, you again reach over here. And from our childhood, the angle that we know that a one circle revolves or one circle completes is twice pi, right? We know this thing. So from our childhood, the typical angle measurement that we have learned is essentially mechanical angles. Okay? All the angles that we know. If I tell you that how much is this angle, so all of you will say, sir, this is 90 degree, right? Very obvious. So these are all mechanical quantities. These are not electrical quantities, and these are fine. We deal with these mechanical quantities in our day-to-day life, which is fine. Okay. So the bottom line I wanted to clear over here is that irrespective of the configuration of your stator, okay, again I'm repeating, irrespective of the configuration of your stator, one complete rotation of your rotor will give you twice pi angle. Is it clear up to this?
Yes, sir.
Okay, fine. Okay. I mean, it will be better, okay, if you can at least respond so that I will know. And you guys, you are responding, so that's good. Okay, now let us try and understand what is the corresponding electrical angle for a two-pole system. Right. So now, if you assume this to be one end of your conductor, then say your conductor, the other end is over here. Okay, so let's give a dot. Say that is a dot and this is a cross. Assume like that. So if this is the scenario, at this specific position, we know that the rotor is continuously rotating, but let us just try to fix its position at this particular configuration now. So at this point, tell me, what is the flux linkage between your north and south pole, or between your stator and rotor, or with this specific conductor? What is the flux linkage? Do you remember the concept of flux linkage? When linkage is maximum and when linkage is minimum? Do you remember that? Come on, you can at least try. So what is the flux linkage, or how do we determine the flux linkage?
So the linkage is maximum when the rotor is horizontal and minimum while vertical, I think.
Right. All right. Yeah. I mean, that is true. So what we do is we know that it is maximum when the plane of your conductor and the magnetic field are perpendicular to each other. Okay, that is when you have the maximum flux linkage. I mean, you can just review it. But for I mean, the same thing, if you want to get it in simple terms, we can say that if your conductor is parallel to your magnetic field, then the flux linkage is minimum, or the flux linkage, there is no flux linkage at all, because the angle becomes zero. Okay. So now, if the flux linkage is zero, how much current will flow through the conductor? Definitely. So how much current will flow through the conductor?
So no current.
No current will flow. Very obvious. That means when you say this is your position 1, when you are in position 1, this is your electrical position 1. That is, you are not getting any current, or the flux linkage is zero. In whichever analogy you understand, it's fine. Okay. Either way, it will always become zero. Now, as we said, the rotor will keep on rotating. So as the rotor will come in this position, say position number 2, now you see, if your conductor is like this, now the plane of the conductor and your magnetic field, or just you can say that whatever your friend said, that if the conductor is in horizontal position and if a magnetic fields are vertical, then that is where you get your maximum flux linkage. So if in position 2 you get your maximum flux linkage, that means what? In this current diagram, you will get your maximum current, isn't it?
Yes,
Yes,
sir.
sir.
Is it okay?
Yes, sir.
That means this is your position number 2. Then again, as you move away from this position and you end up in position 3, then again you have got the same configuration. So you reach over here, that is position 3. When you are in position number 4, you are in the complete reversal of position number 2. That means what? You will still have the maximum linkage, but the direction will be in opposite direction. So that means this is your position number 4, and finally this is again your position number 1. So for a two-pole system, I can say that my theta m is equal to my theta e. Let me know whether you understood up to this or not. Is it clear up to this?
Yes, sir.
What are the takeaways? So what are the takeaways from here is, see, when you go from north to south, okay, when you go from north to south, your electrical angle measures 90 degree, or sorry, your electrical angle measures 180 degree. Again, when you go from south to north, you go another 180 degree. Before, I mean, while discussing the magnetic angle, I told you that, or while discussing the theta m, I told you that your theta m is not dependent on the stator, is not dependent on the number of poles that you have. One complete revolution of your rotor will always give you twice pi angle. There is no deviation from that. But now you see that when we come to our electrical angle, it is actually related to the number of poles, how many times we cross north south north south north south. That is what dictates what will be my electrical angle. Is my last statement clear?
Yes, sir.
Yes, sir.
Fine. So now let us see what will happen for a 4-pole system. Of course, it's written already over here, everything. I mean, the graph should have been hidden on the first case. So again, tell me, when you are in position 1, you will have maximum linkage or minimum linkage? Just tell me in this manner, maximum or minimum?
Minimum.
Minimum linkage.
Minimum. When you are in position 2, you will have maximum or minimum?
Maximum.
Hmm?
Maximum linkage.
Maximum, everyone, you agree that it will be maximum?
Also minimum.
Minimum, sir, in the
Minimum.
opposite direction.
Right, it will be minimum in the opposite direction. Is that point clear? I intentionally did not give point 2 over here. This is where you will actually have your maximum, and this is your point 3 where you will have your minimum, right?
Yes,
When
sir.
you go from north to south, how much electrical degree do you accomplish?
180 degrees.
180. 180.
180, right? That means what? This is your position number 1. This is your now position number 2. This is your position number 3. So similarly, again, this is your maximum, but in the opposite direction of 2. So that means this is your position number 4, and this is your position number 5. See, now, like before, you have already completed twice pi because you have come from north to south, again back to north. So in the previous two-pole system, when you completed from north to south, again back to north, you traversed twice pi distance. So the same thing now. So if you keep on going, this is your position number 6. So this becomes my position number 6. This is my 7 where I will have minimum. So this is my 7. Again, this is where I will have my maximum. So this becomes 8 and this again becomes my 0.1. So how much degree did now your rotor complete after one complete revolution?
So 4 pi.
4 pi.
Right. 4 pi. So what is, and how much is the mechanical degree?
2 pi.
2 pi.
Right? It will always be 2 pi. So one complete revolution of the rotor will always give you twice pi. So you have twice pi. Again, as we have said in the previous slide, that the mechanical degree does not depend on the configuration of the stator, but my electrical degree depends on the configuration of the stator. So now if I give you 6-pole system, 8-pole system, I believe you can find out, right?
Yes, sir.
Any one of you, please, if you have any doubt, any confusion, please stop me and ask again how I'm getting all these things. These are basic physics, nothing complicated, okay? Just basic physics, nothing else. Okay, if that is the case, now tell me what is the relationship between your theta m and theta e? I mean, in this case, at least in 4-pole system, what is the relationship?
Theta E is equal to twice into theta m.
So in 2-pole, we saw that theta m is equal to theta e. When we are in 4-pole, now we see, yeah, sorry, what you said? Sorry.
So theta
What
E
is the
is
relation?
equal to twice into theta m.
Theta e is equal to twice theta m, right? So, I mean, is there any relationship with the poles? I mean, can you generalize the system?
Number of
So
poles
theta
by
E number of
P
poles
by
divided by 2.
Number of poles divided by 2. So what equal to what? Tell me, what will I write? What will
Theta
I
E
write? Tell me.
equals to P by 2 into theta m.
Theta e is equal to P by 2 into theta m. So if it is a 4-pole system, 4 divided by 2 becomes 2. So theta e is equal to 2s theta m, right? So if it is a 1-pole system, so it is 2 by 2, 1, right? So did all of us understand this portion?
Yes, sir.
That theta e is essentially, so that is my electrical angle will be number of poles divided by 2 multiplied by the mechanical angle. So this is the relationship that we had been looking for. Okay, I think, and this is what exactly said. Okay, so this is the relationship that you saw for theta. It is equivalently true for your delta as well as for your omega. So if delta is your electrical angle, then it will be P by 2 into delta m. If omega is your electrical angle, it will be P by 2 into omega m. But giving you visual explanations of delta and omega are a bit complicated. So if you understand with theta, the same is applicable for all the quantities. So that is the relationship that we'll be using now. So you see, we get that delta is equal to P by 2 delta m, exactly what you said, right? You brought this expression. So delta is equal to P by 2 delta m, omega s is P by 2 omega s, omega ms, sorry. So what we had previously, we had h square, h into d square delta m dt square is equal to half omega ms pm minus pu. So now what we can write, or h is h, we can have d square instead of delta m. What can we write? If I convert it to electrical quantities, delta m, what will it be?
2 delta. 2 delta.
P delta E.
2
What is
delta.
the relation? Only 2 delta?
2 delta by P.
Right, it will be 2 delta by p. See, I mean, you can see from this expression over here. Right? So delta m will be twice delta by p. So it will be twice delta. Let's say, okay, let's say divided by p by dt square, okay, is equal to half omega ms. So omega ms can be written as what?
Twice omega.
Omega
4 omega by P.
it will be 2
Twice
omega
omega.
s by 2 omega s by p. From this expression again you can see, right? So omega ms can be written as twice omega s into p into the previous one that I had, pm per unit minus pe per unit. Okay. So what are the simplifications that we can do to get this format? So we can write d squared delta. I can take the 2 outside. I can keep the p over here. I can make it dt square. I can take the h on this side now. So 1 by twice h twice omega s by p and say pm minus pe per unit. So now let's see if we can cancel out a few things. So these two and these two gets cancelled out. This p and this p gets cancelled out. So if I take these two at this position now, and then I end up getting this expression, that is d squared delta by dt square is equal to my omega s divided by twice h into pm minus pe. So this is my swing equation. Is it understood?
Yes, sir.
So if I ask you now, what is d squared delta by dt square in terms of the rotor, what do you say? What does it give? D squared delta by dt square in terms of rotor, or from the point of view of rotor, what do you get from d squared delta by dt square?
The rotor speed.
Angular
A bit
acceleration.
more.
Acceleration, sir.
Excellent. Right, very good. Yeah, I mean, you are there, I know. So it's rotor acceleration. So you see, you will have some rotor acceleration, or it can be deceleration as well. So you will have some sort of acceleration or deceleration only when you have a mismatch between your mechanical input power and the corresponding electrical power. Okay, only if there is a mismatch you will have some rotor acceleration. Otherwise, you will not have any kind of rotor acceleration. That is, your delta will remain fixed in time and you will not have any kind of acceleration. The velocity will remain constant. So this swing equation essentially helps us know about the rotor acceleration. Now, what is the order of this expression? First order or second order?
Second order
Second order.
differential equation.
Second order. Have you, I mean, did you had the course numerical methods?
Yes, sir.
Yes, sir.
So that means you are familiar with Euler method, Runge-Kutta method, right? All these methods you are familiar, isn't it?
Yes, sir.
Yes, sir.
Okay. So tell me, which one was more easier to deal with, second order expressions or first order expressions? Which one was easier to deal with, second order or first order?
First order.
Definitely. I mean, you don't need to have the knowledge of numerical methods to answer this. Definitely, any first order expression is easier to solve than second order expression. So what is our next target is, let's see if you can dissolve this second order expression into maybe two first order expressions. I mean, if you dissolve a second order equation, you cannot have a single first order equation. That's simply not possible. So you need to have at least two expressions or two first order expressions, which will give you your corresponding equivalent second order equation. And that should not be a difficult thing to do. In our previous slides, we showed this derivation. Do you remember that d delta m by dt is omega m minus omega ms? Do you remember, or should I go back a little bit?
Yes,
Okay,
sir.
let me go back. Let me go back. No problem. Here, do you see the term on your right hand side? Here. Right? Do you remember this one? I mean, how did we come over here? We came from here. We know that theta m is omega mst plus delta m. So if you do first derivative, you get d theta m by dt is equal to omega ms plus d delta m by dt. And you told me that d theta m by dt is equal to omega m. So that is how we got d delta m by dt is equal to omega m minus omega ms. Let me write. What was the relationship from the previous slide? We know that theta m is delta m plus omega ms into t. So when we said that d theta m by dt is actually d delta m by dt plus omega m of s, then you told me that this term is essentially what? Velocity, right? D theta m by dt, rate of change of displacement with time. Angular
Yes.
velocity, isn't it?
Yes.
So that is what?
Omega
Omega m. Omega m is d delta m by dt plus omega ms. So from here, we found this expression. Is it okay now?
Yes, sir.
So what
Yes,
we
sir.
get, d delta m by dt is equal to omega m minus omega ms. That is what we'll be using now. So here, d delta m by dt is omega m minus omega ms. So again, we use the relationship that we have. So omega m can be written as twice delta by p. Okay, the previous relation. Okay, if I go back, what is the relation? Delta is equal to p by 2 delta m. So we can write that. That is delta is equal to p by 2 delta m. Similarly, omega m, sorry. Similarly, my electrical omega will be p by 2 omega m. So if you plug in this relationship, then for delta m, you will get twice delta by p, where this delta is now your electrical quantity, by dt is equal to omega is equal to twice omega by p. So this omega, I mean, this was your mechanical omega. Now this is your electrical omega, minus it was omega ms. So now it is only omega s. So in all these cases, your this p and this p and this p gets cancelled out. These two gets cancelled out. So you are left with d delta by dt is equal to omega minus omega ms. Clear up to this? Okay. Now if you do double differentiation, that is d squared delta by dt, then you know that this is constant. So if this is constant, then d omega s by dt will become 0. So what you have, d squared delta by dt is essentially d omega by dt. And in your previous slide, you saw that d omega by dt is equal to omega s by twice h pm minus pu minus pe pu. So what you have, so this is your one single order equation, d omega by dt, but we need the relationship of omega as well with delta, right? On the left hand side, I have got delta. So I need some relationship of omega with delta. And this is my relationship with omega and delta, that is here. So d delta by dt is, so these are your two first order equation, which essentially gives you the same equivalent second order expression of the swing equation that we had. So now you'll see that solving these two expressions, I mean, we will be solving it. We'll use some numerical methods as we move on in the course of the course of our course. You'll see that we will be solving these expressions using some numerical methods. Any question up to now? Okay, no question. That means either you understood everything or you understood nothing. Okay, hope you understood something at least. So now we are moving to a different expression. So again, I'm asking, have you understood up to this? Any question? What was h in this expression? Do you remember? What was h? No one. কারো মনে নেই h কি?
So
Sir,
inertia
H is
constant.
inertia constant.
A constant, right? Inertia constant, and omega s,
Synchronous speed.
the speed.
that is also constant, right?
Constant. Yes, sir.
Right. So we can write that d omega by dt is proportional to pm minus pe, right? We can write that, isn't it? Okay, fine.
Yes,
Fine.
sir.
If you don't have, okay. So these are some small things you should be careful about. Okay. So now what we're interested is, now we have the swing equation, that's fine. Now we want to see if we can have some expression of this PE, electrical power. Let us see if we can have some expression of this electrical power. Few things we know. We know that omega, this omega is the velocity of my rotor. Okay? That's fine. We know that. We know that this is the synchronous speed, which is typically represented by twice pi into f of s, where f of s is your It can be the supply frequency, it can be the synchronous frequency. More specifically, it is your synchronous frequency. So we know that this is given by twice by Fs, or it is again a constant. H is constant, we know that. Mechanical quantity, we are not that much interested. We will get straight away value from for the mechanical quantity. So what we are interested in is the electrical power that we have, output electrical power. So now we'll see some circuits and we'll try to see if we can find the expression for this PE, or output electrical power. So we consider this following circuit over here that we have. So we have a generator represented as E dash. So E dash, if you recall the first SMIB that you saw, the same thing. So from there we know that E dash is the internal EMF of the generator. JXD dash, that is the internal direct axis reactance of your generator. Okay, what is VG, anyone? What is VG over here?
The terminal voltage.
Terminal voltage of
Generator.
Generator.
The
Very good.
generator.
Right, so VG is the terminal voltage of the generator. Then we have got some line impedance ZL. ZS can be some local impedance maybe, so which is, I mean, say your generator is supplying to the infinite bus voltage, that is your bus 2, or and at the same time maybe it is also satisfying some local load, so where the impedance is ZS. The main takeaway from here is that all the quantities written over here are your phasor quantities. That means it will have like V, it is your infinite bus voltage, so these are phasor quantities, so it will have a magnitude. And by default, what is the angle of the infinite bus? What do you assume?
Zero, sir.
Zero, because we assume that is my reference voltage. So similarly, E dash will have a magnitude E dash, and the angle associated is typically delta, right? So VG is again VG with some specific angle, something that we still don't know, and you will see that we don't need to know as well. Okay, you'll see. Then we have my ZL. So now, see, now it says ZL, not XL. That means you are considering impedance. So if ZL is impedance, ZL can be written as what?
Complex number.
How do you
RL
typically
plus XL.
XL? That's what I was expecting. Typically, how we express for a transmission line. So we say it is RL plus JXL, right? Similarly, you have ZS. So it will be RS plus JXS. Okay, so JXD dash, this is purely reactive. So we do, sorry, this is purely inductive. We don't have any reactive portion over there. So that's fine. How many terminal we have? Or how many buses? No, it should be terminal actually. Yeah, how many terminals we have? Or how many? Okay, let's be more specific. How many nodes do we have?
4.
3.
3, sir.
3 or 4?
Sir, 4.
3, sir.
It will be 4. It will be 4. Because 0 is, this is your reference node again. Okay, so we need a reference node. So this is your reference node. Then you have your node 1, rest are marked, node 2 and node 3. Few things to understand over here, that is node 1 is actually the internal terminal of the generator. Okay, node 1 is the internal terminal of the generator, and node 3 is the external terminal of the generator. So your generator is actually consisting of this much area. Okay, so this is what represents your generator. What is the relationship between E dash and VG? Are they equal?
No, sir.
No. Are they ever equal?
No, sir. There are losses.
So they are never equal. Okay. If your generator is not loaded, okay, so if your generator is not loaded, you will see that your E dash and VG is essentially the same. Once your generator is loaded, then you start losing some power. Then you will see that your E dash is not typically, your E dash is always greater than your VG. But if your generator is under no load condition, I mean, this is something you should know. I mean, definitely you have learned, but probably you forgot. So if you are in low load condition, then your internal EMF and your terminal voltage becomes the same. Okay. So can I say that this voltage source is giving some amount of current from here? Can I say that? Say this is I1. Can I say this thing?
Yes, sir.
Okay. Again, if you are assuming this voltage to be infinite bus voltage, I can again assume that some current is coming from here as well, from node 2. Okay.
Yes, sir.
If you agree up to this, then the next thing will be or should be a bit more understandable or a bit more easier to comprehend. That is this one. What we want is this is not mandatory. Okay, the next circuit that you will see, it is not mandatory for you to go over there, but according to the author, if you convert this system to the equivalent current injection model, then the calculation becomes easier. But again, you can apply your circuit knowledge from this circuit, and if you can derive the same expression for PE, no one has any problem. Okay? You can do that. But according to the author, if you convert the left hand side figure to your corresponding right hand side figure, then the calculations become way more easier. So what did the author, so what did we do in the current injection model? Instead of taking voltages, now we are assuming that currents are being injected into the nodes. The same assumption that we saw in the previous slide. So now we are assuming that I1 is being injected to node number 1, same as this. Okay, in node number 1, we were having I1, and the voltage of your node 1 is still E dash. Then in node number 2, I2 is being injected, and the voltage is still the infinite bus voltage, that is V. But now this was my terminal characteristics, that is the node characteristics. So we are more interested in the rest part of the circuit other than the node. So how did we come from the right hand side figure to this side figure? Any idea how we came from what? How we derived or how we came to this current injection model? Anyone? What do you think? Both the
Sir,
circuits
Y
are
to
same.
delta.
equivalent. What again?
Y to delta.
Y delta.
All of you sure it's Y delta? If you are giving answers of something, you should be confident. If I repeat the same question again, why do you get confused?
In the lab class, lab we were taught.
Lab এ?
Lab দেখাইছিল sir.
Oh,
Why?
এটা lab. Oh, আচ্ছা। আপন দেখাইছে already.
Yes, sir.
Okay, fine, right? Yeah, it is Y to delta conversion. Okay, so you see, essentially, this is your Y circuit. So let's just give boxes. So you know the formula, I guess, as well. Okay, so this is your JXD dash, this is your ZL, this is your ZS. So this is your Y configuration. So from here, you are supposed to reach to delta combination. So typically, how do we express? We assume that, say, this green color is my corresponding delta. So these are connected. These two are connected. Okay, and finally these are connected. So say if I say this is Z1, Z2, and this is Z3. Let's see. So tell me, what is Z1 equal to? Convert from Y to delta. So we are going from Y to delta. So now tell me, Z1 is equal to what? Anyone? Simple Y delta conversion. এগুলো এখন আটকে গেলে কেমনে হবে? Do you remember the formula or you forgot? And at least you can say that, sir, we forgot the formula, right?
So at the numerator there will be the multiplication of 2 JXD Z3 JXL JXD ZL and ZL Z3
So it will
divided
be JXD into ZL plus
plus
ZL ZS plus ZS into JXD
JXD.
dash. Okay, divided by
Sir, Z1 ZL, sir.
ZL. Very good. So what we have when we are deriving for this one, the opposite Y connection becomes the denominator and every other combination comes as pair product. Fine. So this is how we get Z1. Similarly, you can have Z2. Similarly, you can have Z3. So that is exactly what they got. Just they named it in a bit better way so that it's easier to understand. So they named it Z12 because it is connected between node number 1 and node number 2. They named it Z10 because it is simply connected between node 1 and node 0. And they named it Z20 simply because it is connected between node number 2 and node number 0. So our Z1 is equivalent to which impedance over here on the left hand side? The Z1 we calculated. This is equivalent to which impedance on the left hand side?
Z10.
0.
Very good. Z10. So this is what we got. So I can simply write that this is equal to Z10. But they have written that Z10 is equal to 1 over Y10. What is Y10?
Admittance.
Admittance. Very good. So what do you get as your admittance? If I want to write the admittance, what will I get?
ZL over the 1 by Z.
Right. So ZL divided by this entire term. So that is your Y10. So I can write that Z10 is essentially 1 by Y10. Is it okay, everyone? Any
Yes,
confusion?
sir.
Hmm.
No, sir.
Okay, fine. Good. So all the expressions are given over here. So you have got your circuit. So from Y configuration, we are going to delta configuration. In the delta configuration, we now get all the equivalent impedance. The only difference is instead of writing it as impedance, we are using admittance. You'll see, I mean, it's better. It is that there is no hard and fast rule. You can keep it as impedance as well. If you know impedance, if you know admittance, then doesn't matter what you use, all will give you the exactly the same thing. So we are clear about the current injection model, right? Now, how many nodes we have?
3 nodes.
How
So
many
3
nodes?
nodes.
Right,
sir.
very good. So now we have got 3 nodes. We eliminated the node number 3 from the initial model. So from our initial single line diagram, we used delta Y conversion, or to be specific, we used Y delta conversion, and we eliminated node number 3 to get the simplified current injection model. Okay. So now what? Now we need the expressions for I1 and I2. Anyone? Can you tell me how we got I1? What did we apply? Which theorem, which logic, what knowledge of your
KCL.
circuit did KCL where?
On node
In which
1 and
node?
2.
Simultaneously?
1 and 2.
For I1, it's node 1.
Okay, so when you are applying KCL to node 1, what is happening to I2 of node 2? Because I don't see any I2 in the node 1 expression of your KCL. What happens to that? You learned something, right? That you can eliminate one source, calculate for the other one, again eliminate the first one. Remember that, right? There is a specific name for this
Superposition,
principle.
sir.
Very
Superposition
good.
theorem.
Superposition, right? That is the first thing. First of all, we apply superposition principle. Then after applying superposition principle, then we apply the KCL. So let me break it down a little bit because I'm not sure that whether all of you are understanding or not. So initially what we do, initially we forget about I2. Okay, so we forget about that. So if I want to apply KCL in node number 1, so this is your I1. Let us assume over here I have got I dash. Over here I have got I double dash. So what? Applying simple KCL, I can write that my I1 is actually I dash plus I double dash. So can someone tell me what is I dash equal to? I dash is equal to what?
So E dash minus V into Y12.
E dash minus V. Okay, say if I want to write in terms of impedance, I'm trying to keep it as simple as possible. So this is my I dash. I mean, no one should have a doubt about how we got I dash. Plus I double dash. So what will be my I double dash? E dash
E dash
minus
zero
0
by Z10.
Z10. Very good. So from here, as we see that there are admittance, so I'll try to remove the impedance. So how I can remove the impedance? Just 1 over Z12. So E dash minus V multiplied by Y12 plus E dash into Y10. Now I can simply take common. So if I take E dash as common, what do I get? I get Y12 plus Y10 or Y12 plus Y10 and minus V into Y12. So this is exactly the same expression that we have over here. So you apply the same principle, you apply the same logic. Next time you remove I1 and then you apply KCL at node number 2 for I2, and you get the expression for I1 and I2. Clear up to these two expression? Clear, everyone?
Yes, sir.
Anyone who wants me to show you how we got I2? If you want, I can show that. Anyone who needs that? If you want, you have to speak up. Okay, that means you know. Then we form the matrix. Very obvious. I1 and I2. So I1 is equal to, I mean, these are functions of my E dash and V. So E dash and V are written over here. So what I get, I dash is equal to Y10 plus Y12 multiplied by E dash minus Y12. So minus Y12 multiplied by V. Similarly, I2 is minus Y2 into E dash. So minus Y12 into E dash plus Y20 plus Y12, Y20 plus Y12 into V. And that's how we get the matrix formation. What is this one? Anyone? What is this? What is this called?
Y bus matrix.
Very
Sorry,
good. So this is
impedance.
called Y bus matrix. Etar equivalent তুমি ইয়ে করে আবার impedance করতে পারো. That's fine. So this is something that you learned in your power flow analysis, right? Y bus formation of Y bus matrix. I think you had just some relationship between the diagonal elements. What is the relationship of the diagonal elements? How did you develop the diagonal elements for a Y bus matrix? Let's see how much you remember.
So summation of
The
all
summation
the
of
admittances connected to a particular bus.
Connected to a particular node or bus. Okay,
Oh,
fine.
yes,
Same thing. Yes.
yes.
Yes. So it is the Y bus entry for all the connected admittance connected to that single node. So you can relate that. So your Y11 is essentially the sum of all the admittances which are connected to your node number 1. So what are the admittances? You have Y10 connected to node 1. You have got Y12 connected to node 1. Again, for Y22, the summation of all the admittances connected to node number 2. So again, Y12 connected to node number 2, and now you have got Y20 connected to node number 2. So you have got Y22 is essentially Y20 plus Y12. And what about the off diagonal elements?
we put
Sir, the
according to
admittance
position.
between two buses.
Again, repeat again.
Sir, for Y12, we will take the admittance between bus 1 and bus 2.
Negative of the admittance between bus 1 and bus 2, right?
Sir, negative.
So you take for Y12, you take the negative of the admittance connected between node 1 and node 2. So finally, if you form your matrix, then Y bus matrix becomes what? A symmetric matrix or asymmetric matrix?
Symmetric matrix.
Matrix.
Very good. Thank you. So this is your Y bus matrix, which is fine. So if you know your Y bus matrix, you know the expressions for Y10, Y12. So we don't have any problem with my Y bus matrix. The thing to remember is these are what? Phasor or scalar?
Phasor.
Phasor. These are again phasor or scalar?
Phasor.
Phasor, right? So from these phasors, next we need to find the power. And actually, I'm more interested in showing you this derivation in the class rather than online, because if I'm in the class, at least I can see some of your faces. In the online, I don't know how many of you are actually paying attention. So I think I'll stop over here. At least you know up to this much. Then the expression of power, from the expression of power, we'll start in the next class. How was your quiz, by the way? Let me stop recording. Anyone has any question? Then I can stop the recording. Okay. No question. I can move the pause. Let me